The purpose of the following questions is to get a feel for how to compare and contrast when we're dealing with a sampling distribution and when we're not, as well as getting a feel for what values are usual for the summary and which are not, given a description of the population we're sampling from. And so we're going to do questions that involve the sampling distribution and sometimes when they're not. So we want to understand the difference between these two. The distribution of yearly salary. And again, I want to remind ourselves that we have these formulas. I'm going to write them up here. The means are equal to each other, okay? And the standard deviation, I'm going to use the function notation. SD of x bar is going to be standard deviation of the population divided by the square root of it. So the distribution of the yearly of salary at a company is right skew. And there it is. It's the right skew distribution. That's the distribution of yearly salary. The mean is 35,000. So this is the population mean for salary. So E of S is 35,000. And the standard deviation is 5,000. Again, notice there's a sigma thing. I'm going to use the function notation here. SD of x is 5,000. If you take a simple random sample of 100 employees, what is the approximate probability that the average of the 100 employees' annual salary is lower than 34,000? Okay, let's read this again. If you take a simple random sample of 100 employees, okay, so what am I doing? Let's create a picture of this. I'm sampling 100 from this population. So I'm going to go take, just like you saw in the simulator. I'm taking numbers 30, 33. And then what's happening? Well, from these 30 numbers, I'm now creating a distribution of means. S bar. And what is true about this distribution? Well, the question is what is the approximate probability that the average of the 100 employees, so the average of the 100 employees means that, what am I doing with my, I'm thinking, where did I get 30 from? 100. The average of the 100 employees is lower than 34,000. So I'm taking a sample of 100. And what am I doing with this sample? I'm calculating S bar. What is the center of this distribution? Well, it's going to be 35,000. And the symbol for this is going to be E of X bar, because this is the sampling distribution of means. This is at a single value. This is the mean of just single numbers. This is the distribution of taking 100 numbers and each time calculating the sample average with that 100 numbers, creating a new distribution. Okay, what's the standard deviation of this population? Well, according to theory, SD of X bar will be the 5,000 divided by the square root of 100. The square root of 100 is 10. 5,000 divided by 10 is 500. So be $500. Fantastic. When you do these questions, you should be doing exactly what I'm doing. Understand the population of sampling. Draw a little arrow just to show some kind of process taking place. Draw the sample size. Then we start drawing the distribution. But notice what I have here is a number line. What I'm after is the annual. So what's the chance that the average of 100 employees' annual salary is lower than 34,000? What's the chance that it's 34,000, my average, or less? So this is S bar. What's the chance that it's in this direction? Okay, so I have this number line, I have the mean, I have standard deviation, and what's the shape? Well, clearly this is 100 employees. That meets the criteria we had earlier. This is definitely, I'm going to call this, severe right skewed. And if it's almost always bigger than 40 or 45, we are okay. We're 100, we're more than okay. Okay for what? To say that this distribution is approximately normal. I'm not sure why I'm doing this, since that's the approximate normal. And so really what I want to calculate is, what is this chance? So now I'm going to set things up. Oh, how do I know that this is 35,000? Because I am assuming that the simple random sample is, of course, unbiased. And that's why I'm putting 35,000 here, because this was 35,000, this being the population mean. Okay, keep doing S, X, because I'm so used to X, but I committed to calling this S. So I need to commit here. Fantastic. So now I'm going to do the same thing we did when we were calculating normal probabilities. I'm going to set this up. What's the chance that my average of the 100 numbers, which I'm going to write that part down, is less than 34,000? That's the question. I'm going to come over here and let's just do a calculation. Let's turn this 34,000 into a Z-score. Standard deviation now, I keep recalculate it, it's no longer 5,000, it's 500. So I see that when I do the calculation, this is going to give me -2. So what I'm after is the probability that the sample average of 100 is less than 34,000, which translates to being the z-score of -2. And again, I have two ways of doing this. If I'm using the 68, 95, 99.7 rule, remember what this is saying is we're two standard deviations on either side. This is 0.95, but all I'm after is this little part. Together, these two tails make up 5%. So 5% plus the 95 gives you 100. This whole thing is 1. This area total is 1. So this answer is going to be 5% divided by 2, or 0.025 using 68, 95, 99.7 rule. Now, what is it if I use a GeoGebra? Online, did GeoGebra Classic. I got to this screen here. This thing popped up, and I want to want its probability. Should this go away, remember, if this goes away, then come back to these three marks called a hamburger, go into View, and click off Probability Calculator, which is what you want. So the default when you take Probability Calculator is to go immediately into this screen right here, which is great. So all I'm going to do is I want less than. I entered what I want is -2. And I can see that using technology, it is not 0.025, it is 0.0228. Using technology, using GeoGebra in this case. So what happens? What's the likelihood of getting an average of 34,000 or less if you average 100 employees? It's not very good. It's about 3.28%.